Let's return to the following context. A point travels along a circular path that is centered at the origin for one full lap. Now, let's let the variable d represent the distance the point has traveled. Since the point's distance to the right of the vertical axis is a function of the distance the point has traveled, we can define a function f to represent the point's distance to the right of the vertical axis in terms of the distance the point has traveled. I have these values shown here, and as the point travels, we can track d and f of d. So as the point moves, d and f of d vary together. Now we can actually track these graphically as we've done before. So let's represent values of d on the horizontal axis and values of f of d on the vertical axis. And as the point travels, let's keep track of the point d, comma, f of d. If we do this and we trace this point, a graph emerges that shows how d and f of d are related. Now in a previous video, we decided that the vertical intercept of f was 3, because f of 0 is equal to 3. We also decided that the graph has a couple horizontal intercepts, one at d equals 4.71, and one at d equals 14.14. And these are values of d that produce an output of 0, or values of d where the graph of f intersects the horizontal axis. Now, we also decided that the domain of f was all values between 0 and 18.85, because this is the set of values that it makes sense to input into f. So the domain of f was all values of d that are greater than or equal to 0, but less than or equal to 18.85. We'd also decided that the range of f, which is the set of all values that make sense as outputs of f, was all values between -3 and +3. So the output, f of d, could vary between -3 and +3. Now, the actual function formula for f is given by f of d equals 3 times sine of d divided by 3. Now, you don't need to know what sine is or any of this. This is just the formula for f, and if we ignore the context, the graph of f looks like this, and it goes on forever in either direction. So the domain has no restrictions, but the output still varies between -3 and 3. So somehow it looks like our domain changed for f, and we should be careful to make this distinction. So if we need to make a distinction between the domain and range while looking at a context versus without looking at a context, we're going to use two terms to make this distinction. We'll use the terms practical and general to make the distinction between when we're looking at a context and when we're ignoring a context. So we'll say that the practical domain and range are really just the domain and range that we've been looking at when we're considering the context. Now, if we ignore the context, we'll use the term general domain and general range. So let's go back to this context we've been looking at. We decided that the practical domain, or the values of d that we can input to f within the context of the problem, was all values of d between 0 and 18.85, and the practical range was all values between -3 and +3. However, if we ignore the context and just look at the general domain and general range, the general domain was all real numbers. There were no restrictions on the input, and the general range was still the same. It was still all values between -3 and +3. In this course, we will generally be concerned with the practical domain and range, but it's important to take a second and decide whether you are thinking about the practical or general domain and range when thinking about these two ideas.